So we'll be looking into criteria for spontaneous change. We have been looking into things like exergy. So now we'll be looking into criteria for spontaneous change. Okay, so we have seen from previously from the first law of thermodynamics, that is, we have seen what TS equations are. We have seen two TS equations as we have seen here. This is obtained from combining the first law and second law of thermodynamics. It is the first law of thermodynamics. We had delta Q into du plus PdV. This is for a closed system. Whatever we are seeing is for a closed system. And for this is in terms of internal energy, and in a general case, for in terms of enthalpy, we can write dH minus VdP. Okay, I'll put a small q. Just whatever I represent is for specific quantities. So and from the second law, this is from the first law, and from the second law, we had delta Q Yt for reversible process is equal to Ts. But in general, this Cauchy's inequality, this is a part of the Cauchy's inequality, but in general, according to the Cauchy's inequality, we can write delta Q by T is always less than or equal to Ts. And by combining the first law and the second law, that is the Cauchy's inequality, we can write the combination of the first and second laws, these things. That is, first is we can write from this thing, we get delta Q should be less than or equal to TdS. And so we have du plus PdV should be less than or equal to TdS. So we're bringing ds to the other side, TdS du plus PdV minus TdS should be less than or equal to 0. So this is a generalized equation. Okay, so and if we consider the second thing, this thing, we get dH minus VdP should be less than or equal to TdS, or dH minus VdP minus TdS should be less than or equal to 0. So we will just look into what are the criteria for spontaneous change. Okay, we have seen two generalized equations that are obtained from combining the first law, second law, first law and the second law. This is the first equation, and this is the second one. Okay, so if we just look into what happens or how can we predict the direction that a process may go, by using these things. So when we dealt with entropy, we said entropy or S is a key factor in determining or deciding in which direction a process may go. So here we have just written two equations by combining the first law and second law, which gives us a better idea on what all parameters are there which decide in the direction that a process may go. Okay, so by using these, we'll look into certain special cases. Okay, we'll take some special case examples. So first is the example for an isochoric and isentropic process. So if the process is an isentropic, these are special cases. These are all special cases. So we'll be looking into what happens if we are taking an isochoric and an isentropic process. So if we have an isentropic and isochoric process, then dV would be equal to 0 and ds would be equal to 0. In that case, we will have du from this equation, du for an isochoric process and an isentropic process should be less than or equal to 0. So for an isochoric and an isentropic process, or if a process is both isochoric and isentropic, if a process is both isochoric and isentropic, the directionality of the process is governed by this equation. That is du at constant volume and constant entropy should be less than or equal to 0. So the reaction will proceed in whichever direction the internal energy is reduced. Okay, so this is just like something like this. So if we approach from this direction or this direction, if the internal energy is minimum, it tends to go there. Okay, this is a special case. So again, we'll consider 1, 2, or 3 more special cases. The second is isobaric and isentropic. So in case of an isentropic process, again, S is a constant, so ds is 0. And in case of an isobaric process, dp is 0 because pressure is constant. So we'll apply this into this equation. And as dp and ds are 0, we get dh at p, s should be less than or equal to 0. So if the process is both isobaric and isentropic, this would mean that the direction of the process would be, or the process would tend to go to the direction where it minimizes the enthalpy of the system. Okay, so we can see that in these two cases, the directionality is, as we have isentropic process, the directionality is not governed by entropy. Okay. Entropy does not play any role in these two special cases, but in general it does. Okay, we'll look into free energies. So before looking into free energies, we'll look into another special case in which the process is isochoric and isothermal. So this is quite significant. Okay, this can be achieved, especially in case of boiling or melting. If we have an enclosed container, we have a fluid and we add heat to it. We'll look into pure substances. In this condition, when the fluid reaches its saturation point, okay, so the fluid tends to boil, or the liquid tends to boil off, and when it boils, the temperature remains constant. The temperature remains constant. There will be no increase in temperature. So as we have enclosed volume, the volume too remains constant. So this is a practical case. So in this practical case, we can see for an isochoric process, the temperature is a constant thing, and the volume is also a constant. So we can rewrite this equation as d of u t constant s should be less than or equal to 0. This is because we had du du plus pdv minus tds should be less than or equal to 0. As we had a constant volume process, dv drops out. So we have du as t is a constant, d of t constant, s should be less than or equal to 0, or d of u minus t constant, s should be less than or equal to 0. This thing, u minus Ts is called as the Helmholtz free energy, okay, which is usually represented by A or F. This is a specific quantity. This is an extensive property. So extensive property is represented by the capital letters. Intensive property is represented by small letters. So the extensive property A or capital F. So in that case, for a process which is undergoing an isochoric and isothermal change, the Helmholtz, it proceeds in the direction such that the Helmholtz free energy is minimized. Okay, so as we can see here, so dA at constant volume and temperature should be less than or equal to 0. Helmholtz free energy is minimized. Okay, again we have one more special case. This is also very significant because almost all chemical processes and spontaneous processes in real life are performed at constant pressure. Okay, so isobaric and isothermal is, although it's a special case, it is a much more generalized special case. So we already had an equation of, if we have an isobaric process, then dP is 0. Isothermal, dt is 0 or T is a constant. So we already had dH minus VdP minus TdS should be less than or equal to 0. So as we have our isobaric process, dP term drops out. So we are left with T of H minus T. Yes, should be less than or equal to 0. This term is called as the Gibbs free energy. Okay, so if we have an isobaric and isothermal process, the Gibbs free energy, the process proceeds in the direction such that the Gibbs free energy is minimized, or dG should be less than or equal to 0. Okay, so we can see that in most cases, entropy is not really the driving term. Entropy, internal energy, enthalpy, the Gibbs free energy, which is a composite function, the Helmholtz free energy, which is also a composite function. These are the driving factors, or these things will give us a measure on which direction a specialized process is going on. Okay, so although we have mentioned, or we have derived the Gibbs free energy, the Helmholtz free energy for this is for isochoric and isotherm. This is for isobaric, isotherm. These can be modified or can be used in various cases. So we have A is equal to U minus Ts and G is equal to H minus Ts. So by combining these two, we get G is equal to A minus PV. So these two terms are also related. So before going into the spontaneity of the process, so we have seen a generalized, or not a generalized, a specialized case of, we have seen 4 specialized cases of spontaneity. 4 cases of spontaneity. So we'll look into how we can predict spontaneity in a more general way. So to predict spontaneity in a more general way, we have 4 potentials. As I've said, spontaneity or the directionality of the process is in the general way is attributed to the entropy, the internal energy, enthalpy, Gibbs free energy, and the Helmholtz function. So these things, the internal energy, this is not the internal energy, this is the enthalpy, the Helmholtz free energy, and the Gibbs free energy. These 4 things are called as 4 potentials. Okay. Usually for a process to occur spontaneously, they are minimized, or the process proceeds in a direction in such a way that the potentials are minimized. Okay, there is a lot of redundancy built into this. So usually, if we go for any one of these things, Helmholtz or Gibbs free energy or Helmholtz free energy, we'll get a very good idea on which direction the process is going to happen. Okay, so these potentials can be written in terms of their differential form or written in their differential form. So this will give us the 4 TS equations. Which is the basis for so many things to build, like the Maxwell's relation, like the Cloche's Clapeyron. So these things give us an outline or provide the basis for all these things. So these things are all generalized. These things are not for any specific quantity. These things are generalized or can be applied for any process. They are not limited. Okay, it can be reversible, it can be irreversible. They can be applied to anything. Okay, so we'll look into one more term that is called as a chemical potential. So chemical potential is the amount of energy added to a system to add a particle to a system. So it is very crucial, or it is a parameter of interest in most probably in systems which are undergoing chemical reactions or phase changes. Okay, so if we have like a system which is undergoing a chemical reaction from A to B, or A plus B gives C plus D, gives C and D. Okay, so it may proceed in this direction, it may achieve equilibrium. Everything depends on not only on their energies, but it depends on the pressure, depends on the temperatures, etc. Okay, it depends on the partial pressure properties. Okay, so the chemical potential encompasses these terms, like it defines in a process. In a process, the chemical potential defines the direction in which defines the factors which drive the equilibrium. Okay, so if we include the chemical potential mu, and dn is a change in number of species. Change in number of species. So we can write the 4 potentials, the differential form of the 4 potentials. In this form. Okay, du is equal to TdS minus PdV plus mu dn. So these are all 4 potentials. They all have the units of energy. Okay, the chemical potential is also defined as the molar Gibbs free energy. Okay, mu I, dou G, dou Ni, T, P, and J. So these are constants. So when the temperature and pressure and the number of other species are held constant, the chemical potential is defined as the change in Gibbs free energy for a change of one of the species. So if we have A, B, C, and D, we have A, B, C, and D, we'll fix, say, to find out mu A, we fix the number of species of B, C, and D. So this will be dou G by dou Na when these things are fixed and the temperature and pressure is fixed. Okay. So what is the significance of the chemical potential? So the chemical potential and these free energies or the four potentials. The chemical potential along with the four potentials define equilibrium, define the criteria for equilibrium. Okay, so we have seen whatever we have seen till now. We have seen the direction that a process may go to, or the process may proceed to. That depends on the negative sign, or the inequality. Okay, it proceeds to the direction whenever the potential is, or the direction to which the potential is going to drop. So dG is going to drop, dA is going to drop, or the change in potential is negative. In those conditions, we haven't talked about equality sign. So what happens if we have an equality? What happens if if we have a system A and a system and surroundings B, and if we measure the say the Gibbs free energy, and we got dG is equal to 0. So this defines the criteria for equilibrium. So at equilibrium, the potentials will be the same. So if we just draw a graph, something like this. So this will be the equilibrium point. So at the equilibrium point, the system can't go anywhere down. It has the least amount of energy, or the least amount of potential, or the least potential that we have computed. So that means whichever direction we approach from, or whichever direction the process is going to happen, it has the least potential. Least potential in the sense dG or dA or du or dH will be equal to 0. Whatever parameters we are computing will be equal to 0. So the potential of the system somewhat approaches a dead state. The system can't drop from there. This defines a point of equilibrium. So what is this? How is this significant? This is very significant in case of chemical potentials. So if we consider something like in a very general form, if we consider something like if we consider something like we take a container containing water. We take a container with water and we drop some salt crystals into it. So we know by experiments that the salt in solution has lower potential, lower chemical potential than pure salt crystals. Likewise, water has a lower potential in solution form, or when it has mixed, when it has salt or something mixed into it. So combining these two, the salt will have a tendency to go to solution to attain a lower mu salt solution, and water will have a tendency to take up more salt so as to have lower water solution. Okay, so this drives both these processes to achieve dG less than 0. So this comes to an equilibrium when dG is equal to 0. That is the chemical potential of the solution reaches a cap. Okay, till no more salt can be included in water. This is very significant in terms of phase movement.